look at solving sample test 1 for 244. Consider a system charge is made up of a 2 nanocoulomb charge Q1 placed at 0.5 and a 5 nanocoulomb charge Q2 at 3.43. Draw the diagram, label the charges, and indicate the direction of the field. Okay, we're in the positive first quadrant, positive stuff. We've got the first one is at 0.5. 1, 2, 3, 5. So let's say this one is Q1 and it's -2 nanocoulombs. Alright, and then we will have a 5 nanocoulomb Q2 at 4.3. 1, 2, 3, 4. 1, 2, 3. Something like that. So this one was a negative and this one was positive. Q2, 5 nanocoulombs. Okay, so the diagram, label the charges, direction of electric field at the origin from each charge. Okay, so let's say Q1 is here, so the electric field from Q1, so the electric field is always what a positive test charge at the, it's asking about the origin. So what would a charge right here, positive charge, feel from this -2 coulombs? So it would be attracting it. So the force would be this direction, and so would the field. So we'll call this, let's call this E. Well, let's call it E1 for now. Okay, and then from charge 2 is a positive charge, and so it would repel a positive test charge. Trying to get a straight line here, and so it would push away, and it's bigger, but it's farther away. It's more than twice as far away. It might be about the same size, really. Let's see if we'll make something like this for E2. Okay. Direction of the electric field from each charge. Okay. Draw and label the total electric field at the origin. Alright, so the total field then is these two added together. We can do the parallelogram method here, or do them tip to tail, something. So if this one and then this one goes up, we would have something like this. We could kind of have a parallelogram here. E total. Okay, so that's that one. Solve for the electric field at the origin. All right, so total field is going to be 1 plus 2. You superposition, calculate what the field is from 1 first, and then get the field from 2. Make sure we have them in vector form, and then add them together, and we've got the total. All right, so E1 is easy one. So magnitude-wise, E1 is a point charge. We're going to use a point charge formula. So KQ1 over R1 squared. And then should we just do it as a vector to start off with? What direction does it go? So this is the magnitude. Then we need to multiply it by its unit vector. In this case, E1 goes straight up, so it just gets multiplied by J hat. All right. And so we got, I think we've got everything. And so let's do 8.9876 times 10 to the 9th for K. And then Q1 is 2 nanocoulombs. We're going to take care of the signs with the picture here, so we don't need the negative on the Q1, but we do need the -9 exponent there. So KQ over R1 squared. So what is R1 here? R1 in these formulas in general is the distance from the point charge we're talking about to the point of interest. So it's just this distance along the axis, and that was up 5. And so that is 5 centimeters, so 0.05 meters. This is Newton meters squared per coulomb. This is coulomb, actually coulomb squared. So, did I do that right? Yep, so we're going to end up with Newton per Coulomb, so that's good. So E1 is 8.9876 E9 times 2E negative 9 divided by 0.05 squared. So E1, 7.19 times 10 to the third, but we'll just put that in the units. J hat, and then it's kilonewtons per coulomb. Right, 10 to the third kilo. All right, so there's E1. Now we need E2. E2, again, magnitude-wise, KQ2 over R2 squared. But then unit vector-wise, what is it? So it's going this direction, so it's going to have a negative x and a negative y. We could do components-wise. We've got a 3, excuse me, a 3, 4, 5 triangle, so we can just do ratios, or we can calculate theta here. So if we get theta, we know that this side is 3. So tangent theta, opposite over adjacent. So tangent theta is 3/5. So theta is 3/4. Tangent inverse of 3 over 4, opposite over adjacent, right? So 3/4. And so theta is tan inverse of 3 divided by 4, 36.87. All right, so then we're going to use in here, let's see, so x is the cosine, so we're going to have cosine 36.87 times the x direction vector, but it's actually negative x direction, so we want negative I hat in here. Negative I hat times the cosine, and we're running out of room. And then we're going to have plus sine 36.87 degrees times the y component, right? The sine is the y. And that's also negative, so a negative j hat on that one. We could have also done, well, we know that sine is opposite over hypotenuse. This is a 3, 4, 5 triangle, so sine is 3/5 and cosine is 4/5. And put those in there instead of the sine and cosine, but it gets the same thing. All right, so let's just kind of cheat a little bit and say Q is 5 times 10 to the negative 9 coulombs, and R2, like I was saying, this is a 3, 4, 5 triangle, so this distance, if we didn't recognize 3, 4, 5, we could say that, well, this R2 has to be the square root of the x part squared, 4 squared plus 3 squared. And so that, just to show you, I guess, we can do the square root of 3 squared plus 4 squared, and sure enough, it's 5. Okay, so that's 5. So this R2 is 0.05 squared. Oh, so I was wrong. They're the same distance away. They're both 5 away. So this this one should be quite a bit longer because it's bigger charge. So my picture's not going to be very good. But anyway, we'll go with it. Okay, so we can calculate this. So 8.9876 E9 for KQ times 5E negative 9 divided by 0.05 squared is the magnitude. Let's put that whole thing in parentheses and multiply by cosine of 36.87. So we get 14.38 kilo, but it's multiplying negative I hat, so negative 14.38 I hat minus, and then let's do that same thing again. I'm going to cheat and go get it if I can, and just change that cosine to a sine. Okay. And so we get, so this, because it's a negative j hat, we got this minus sign here, and then 10.79 j hat, and this is also kilonewtons per coulomb because there's this 10 to the third on both of those. Okay, so now we've got both the parts, E1 and E2, in vector form, so we can add them up. E1 has no x's, so the whole x is just this one. So E total is negative 14.38 I hat minus 10.79 j hat plus 7.19 j hat. So this is E2 and this is E1. Doing it backwards, but anyway, so you get negative 14.38 I hat. This is all still kilonewtons per coulomb. And 10.79 minus 7.19, doing the opposite here since I already got in there. So it's going to be negative 3.6 j hat kilonewtons per coulomb is E total. Alright, so the y component should be very, small. X is 14 and y is about 4, so this should be quite a bit longer than how I drew it. But anyway, I've got the right direction. The pictures are mostly trying to get us in the right quadrant. Actually, it's down here, so I'm not even in the right quadrant because this should be quite a bit longer. So then when we make our parallelogram or it should be more like that. So this is really what E total looks more like because I had my E2 too short. E2 should be longer like that compared for that relative to that E1. Okay, so what would the force felt by a 3 nanocoulomb charge? What would be the force felt by a 3 nanocoulomb? All right, so force is just Q times E. So once we've got the electric field somewhere, we can get the force on whatever size charge we have by this equation. So force equals Q, which is negative 3. We'll just go with magnitude and figure out the direction here in a minute. Or should we go ahead and, we can just go ahead and do it. So negative 3 times 10 to the negative 9 is the charge. And so then the force, basically the negative is going to say that the force is going to be opposite direction of E total, and so that the two negatives here, everything's going to be positive, so the force vector is going to have positive components, so that'll be fine. Negative 14.38 I hat minus 3.6 j hat kilonewtons. Let's just go ahead and write 10 to the third newtons per coulomb to get all the numbers working together here. So these are all going to be positive. So we're going to have 3e negative 9 times 14.38 e3. So 43. Yep, it's still going to be a pretty small number. 43.14, and this is going to be micronewtons. 10 to the negative 6 there. And then just do this one, 3e negative 9, just double checking our exponents, times 3.6 e3. Yep. Plus, that one was I hat. Don't forget the vector parts. Plus 10.8 j hat. Again, 10 to the negative 6 micronewtons. Okay. So, tiny little force there. But hopefully got the process. Okay, number 2. A proton and an electron are fixed 2 nanometers apart. The test charge is placed halfway between them, 1 nanometer then. Sketch and label the charges, electric field components, and the total electric field on the test charge. Okay, so we've got 2 charges, a proton and an electron. So we got one is a positive, one is a negative, and the total separation is 2 nanometers. And then we're going to put a test charge in here at 1 nanometer from each in the middle. All right. Label the charges, electric field components, and the total electric field on the test charge. All right, so if we're going to make the minus red, again, test charges are positive, and it's going to be attracted, so its field is going to be like so. We'll call this E sub electron, I guess. All right, and then the proton has the same size charge, but it's positive, and so it's positive. It's going to push away a positive, so it's going to have an E same size because it's the same distance away and same Q, so it's going to be E of the proton is going to be just right on top of E of the electron. They're the same size going that way. And then the total electric field, since everything is all agreeing pointing that way, it'll just be take two of those, or put them tip to tail, or however you want to do it, but the total would be this, would be E total, would be something like this, the two added together. Everything's in the X direction, so we can think of everything has an I hat on it, or something like that. All right, what is the electric field at a point halfway between them? Okay, so if we're looking for the electric field, again, same kind of thing here, E total is E1 plus E2. But it's a little easier now since neither one of them have any Y components, so we can just kind of add them up, and they are actually equal to each other. But let's go ahead and write things out. So E1 is KQ1 over R1 squared, and its unit vector is I hat. So let's just put I hat on there, I guess, to be complete here. So Q1 though is which one? Okay, let's call this electron and proton, since that's what I was doing. So these will be E, E, E. Okay. So the charge of an electron is what? It's elementary charge, little e, right? Which is, I guess let's put in numbers. So K, and then charge of an electron, 1.602 times 10 to the negative 19, divided by R squared. R is 1 nanometer, 1 times 10 to the negative 9 meters squared. All right, and so plugging all that in, E negative 9 in the bottom squared. Just make sure we got that correctly. Looks good. So we have 1.440 10 to the 9th. Whew. Yeah, with such a tiny distance between makes the top big. Newtons per coulomb. I hat. Don't forget the I hat. I really don't, I guess, so much need it since everything is I hat. How about E of the proton? It's going to be pretty much exactly the same, right? Because it's also I hat. It's also got K. Also has the same charge. 1.602 10 to the negative 19 also has the same distance, 1 times 10 to the negative 9 meters squared. So it's going to be the same number, 1.440 times 10 to the 9th newtons per coulomb I hat. So E total is just twice that, times 2. 2.88 we'll go with. Times 10 to the 9th, I guess. I hat newtons per coulomb. Okay. Good. What would be the force on a point charge placed halfway between them? So same as above here, pretty kind of redundant here, but anyway, force is QE. Once you got E, it's easy to get force. And so this one is positive, so 5 times 10 to the negative 9 times 2.88 times 10 to the positive 9 I hat. Coulombs times newtons per coulomb, so we're going to get our force in newtons, which is good. 5. The negative 9 and the positive 9 cancel out, so 5 times 2.88. 14.4 newtons. Okay. Okay, just checking my numbers there real quick. Looks good. Okay. Now, number 3. Write an integral needed to derive the equation for the electric field at a point above a long line due to a long line of charge with linear charge density lambda. Start with dE equals k dq over r squared r hat. So it's like the field for a point charge put into infinitesimal form. And so we have a long line of charge. We have a point above it. Okay? And sketch and label the line, charge in the line indicating dq and r. And so if we just pick some little segment of the line, it's going to have a charge dq, it's going to have a length in there, dl. We may need, if this is our point charge, or it's the point we're looking at finding the field, then we can, the r is always how far the charge is from the test point. So this is r, little r. We could call this how far the point we're looking at from the wire. I don't think it says a name for it. We'll call it A, and if we need it, we can call the length of the wire L, or the line of charge, length of the wire charge L. All right. Are there any symmetries we can use? Why or why not? Well, yes, there is, because if we are assuming it's a very, very long line, infinitely long line, or if we assume we're in the center of the line, we can anyway. Because if we have, say, take this far point, it will have a force this way, and this far point will have a force that way. And so the x components will cancel out. One will be positive, one will be negative, and so only the y parts will add up. So x components cancel. Okay, so we can say e sub x equals 0 or something like that. What is a convenient variable to use as the variable of integration? All right, so we'll assume we kind of have a x and y axis here. And so the thing that's changing as we go through our dq's is x. So I would say x. Because it gives position, I guess, of dq. Write an equation for field, including the integral. You don't have to evaluate the integral. Okay, so we have dE, like it says there, is k dq over r squared times r hat. Alrighty, and so we will need to just take the y component eventually, but let's go ahead and just, well, we'll leave it as a vector. Okay, so what is dq? dq is how much charge is on this little length of the line. So in general, charge density is newtons per coulomb. I'm sorry, coulombs per meter. And so if we're going to multiply that, so it's charge per length, and so we're going to multiply that by the length. And so we will have lambda dl, and dl is a little bitty distance in the x direction, so we could call it lambda dx to get everything in terms of our x variable like we were saying there. All right, so we've got dq in terms of x. How about r squared, or how about r? So what is r in terms of x? Again, r is how far we are from this, is the hypotenuse of this little triangle, right? What is the length of this triangle? Do I want to do it that way? I guess I'll do it that way. So this side is x, maybe positive or negative, and this side is a. So r is square root of x squared plus a squared. Because r is going to be a positive length kind of number, so even if x is negative, it's okay. When a is a constant. Okay. Oh, so r squared is just x, so r squared is x squared plus a squared then. So we've got r squared in terms of x. Now how about r hat? Oh. So r hat is a little vector in here in the direction of r. So we can so if we want to figure out theta here, so we call that angle theta. So we got tangent theta is a over x, and so theta or actually to break up this unit vector, we can do it in terms of x or I hat and j hat. So we can say r hat is cosine theta I hat plus sine theta j hat. All right, because to take the magnitude of this vector, this squared plus that squared, cosine squared plus sine squared equals 1. So that's it's a unit vector, length 1. The x part is the adjacent to this angle theta that I've made here, so it's going to be cosine. All right. What is cosine theta in terms of this? Adjacent over hypotenuse, so it's x over r I hat plus, and then a over r j hat, if that helps anything. I don't know if it helps anything. We want r, we'll have to put that in there. It's going to be a mess. Okay, so r hat is, well, we've got an r in both of them, so we can say x I hat plus a j hat over r, which is the square root of x squared plus a squared. Okay, so E is integral of dE is integral from, I guess we'd say negative L over 2 to L over 2, the way I've drawn this thing, of K dq lambda dx over r squared, which is x squared plus a squared, times r hat, which is x I hat plus a j hat over square root of x squared plus a squared. Okay. Not very pretty. Let me just double check my work. I didn't forget anything here. Yeah, and so since we like I said, by symmetry, we can kind of ignore the x parts because we know they're going to cancel, so we can just kind of get rid of this or say that's going to be equal to 0. Simplify our integral a little bit, but in general, it's something like this. We know these terms are going to cancel out and go to 0, so e is just going to be ey, and we could rewrite it, but I'll just leave it like that for now. Okay, so you need to understand why we need an integral, how to do the dE from the dq, and look at the geometry of the thing to figure out the components. All right, so we won't, it said we didn't need to evaluate the integral, so we'll leave it at that. All right, next problem, number 4. Consider charges arranged as shown. Q1 is 10 nanocoulombs. Q2 is negative 5 nanocoulombs. What is the electric field at the origin? Expressed in vector notation. What force? Oh, this is like the same question we had before. Okay, but it's in it's given in angle notation instead of in x and y coordinate kind of stuff, but we're going to have very much the same thing. So E total, and I guess this is a hint that you need to know how to do these vector problems, either a vector field one, an electric field one like this, or forces. Might have been better to just do it as a force question. What would be the force? A good way to do it would be to say, okay, what is the force at the force of a certain charge at the origin, and then find the electric field. That would be a good variation on this. But make sure you know how to do these kind of problems where you have a couple of different charges and you have to get the field or the force at a certain point or on a certain charge using vectors. All right, so it's going to be KQ1 over R1 squared, R1 hat, plus KQ2 over R2 squared, R2 hat. All right, what are these things? So this is positive, and so it's going to make a positive field down here. Call it E1. Shoot, okay, it's kind of small, but we'll call that E1. It's a big charge and it's close, so it's going to be the biggest one because this is a half-size charge and it's twice as far away, so it'll be like an eighth as big. So I better draw this one small. This is a negative charge, so it's going to attract a positive charge, so we'll have something like this. E2 will be a little tiny vector in here. So again, the two add together, parallelogram kind of thing. So E total will be something like this probably. My estimations are good. Alrighty, so the unit vector for R1 for E1, which is our unit vector for E1, which is R1, is going straight down, so R1 is just going to be J hat, negative J hat, going down. R2 is going to have an X part and a Y part, right? So R2 is going to be cosine 40 I hat plus sine 40 J hat, and they're both positive because it's going up and over. Okay, so E1, E total is equal to, I'm just going to do this one all at once, I guess. So 8.9876 times 10 to the 9th. We can factor that out, or we can put it in both. Q1 is 10 times 10 to the negative 9, and divide that by R1 squared. So R1 is 2 centimeters, so 0.02 squared. And that one gets multiplied by negative J hat. And then We're going to add to it 8.9876 times 10 to the ninth, our K, times Q2, which is 5, times 10 to the negative 9. Again, we're taking care of the direction, sign stuff with the picture, so we don't need that negative in there. And R2 is 4 centimeters, so 0.04 meters squared. And that gets multiplied by cosine 40 I hat plus sine 40 J hat. All right. 8.9876 E9 times 10 E negative 9 divided by 0.02 squared. Okay. 224.7. Negative J hat, and this is going to be kilonewtons per coulomb when we get it. So that's E1, and then this one 8.9876 E9 times 5 E negative 9 divided by 0.04 squared. So magnitude wise, this part is 28.08, 28.09 kilonewtons per coulomb, and so we're going to have to take that times cosine 40 and that times sine 40. So 28.09 times cosine 40 will give us the x component, so that is 21.52 I hat, and then take that same 28.09 times sine of 40, 18.06 J hat. I guess I got my units a little carried away with giving myself space. So this whole thing is kilonewtons per coulomb. We only have one x, but we have two y's. One going up, one's going down. The one going down is way bigger. Alright, so we're going to have 21.52 I hat minus, so negative 224.7 plus 18.06, negative 206.6 J hat kilonewtons per coulomb, E total. Again, you get the two pieces, the one from charge 1 and the other from charge 2. Add them together. The force is QE one times 10 to the negative 9 coulombs times that same thing. I hat so yeah, it's just a 1. So the force is 21.5 I hat minus 207 J hat. And we got 10 to the negative 9 and 10 to the positive 3, so 10 to the negative 6, so micronewtons. Okay. Oh, where did I calculate that? I guess I didn't calculate that part. Okay. I think that's pretty safe to be the right answer. Okay. Let's look at next one. Shown below in orange, an orange cylindrical insulator with radius big R, volume charge density rho is that, blue-green Gaussian surface, radius R, little r. Okay. Not really shown, but anyway, radius little r. And the surface is drawn for the case where little r is bigger than big R. Okay. Write an expression for the enclosed charge in terms of constant charge density, and R everywhere where R is less than, little r is less than big R. So now we're going back to, okay, now we're going to have our Gaussian surface, so we're going to try to figure out the charge inside here. So the Gaussian surface is a cylinder, and so we want to know what is the enclosed charge, Q enclosed, inside a cylinder. So this is an insulator and it has a volume charge density. We'll assume it's a uniform charge density, so the charge is all spread out all inside of there. All right, so how do we get the charge inside, or the charge of the cylinder? Then we'll have little bitty cylinders, or a cylinder that keeps growing in here. It has radius R. So Q is just rho times the volume, right? Volume charge density, microcoulombs per cubic meter times the cubic meters, right? And so Q enclosed is going to be rho times the volume. And what is the volume of a cylinder? Base times the height, right? So the area of the base, pi r squared, times the height, looks like it's L. Okay, I forgot my rho. There we go. So write an expression. So Q enclosed equals rho pi little r squared L. This is for R less than big R. Once we get past big R, then the charge doesn't keep increasing. It only increases as long as we're inside the cylinder and grabbing more and more charge as we grow out. Write an expression for the electric field everywhere that R is less than little r is less than big R. So inside here, what is electric field? Well, if we have a Gaussian surface, so Gauss tells us that the flux is equal to Q enclosed over epsilon naught. Right? We got Q enclosed up here, epsilon naught's constant. What is the flux? The flux is, in general, integral of E dot dA. But if we chose our surface correctly, which we did, then E and A dA are parallel to each other, and E is constant on surface, right? Because the field points out from the center, and the surface is uniformly around the center, and the field points is uniform around the center, okay, pointing out. And so E is constant on our surface, and the surface vector points out, and so does E, so they're parallel. And so the angle theta is 0, and so the dot product just becomes E times A. So phi is just E times A, since we picked our EA cosine theta. Cosine 0 is 1, so I guess I can write that. Right, so that's EA. EA equals Q enclosed over epsilon naught. So that means E equals Q enclosed over A epsilon naught. Q enclosed is rho pi r squared L, and A was the surface area. Well, okay, so we also have these ends. So on the ends of our Gaussian surface, although it's inside here, so it's the little one, the ends, A is perpendicular to E, and so we can also say that, I guess, A or dA perpendicular to E on ends implies 0 there. The flux is 0 on the ends, and so the total flux then out of the surface is just the flux out of the wrapped part, right, the vertical curve part. And so that area is just the circumference of the circle, right? Think of unwrapping it. It's just the circumference of the circle times the height, right? The length times the height. So L times L times 2 pi. The circle that we're talking about is the Gaussian surface, so little r, 2 pi little r, for the circumference of the circle. All right, so it kind of ran out of room here. So E equals, at least magnitude of E. With Gauss, we're assuming we know the direction, so we're calculating the magnitude. We're going to cancel out one of the R's, cancel out the pi's, cancel out the L's. So what do we have? Rho R over 2. Rho R over 2. Okay. Oh, and where did epsilon naught go? Epsilon naught. Rho R over 2 epsilon naught. Okay. And if we want to keep it as a vector, we'll just say in general it's r hat direction, out from the thing. Okay. Write an expression for the electric field everywhere where r is greater than r. Okay, so same argument, same good Gaussian surface. And so on your test, do give me this argument. Tell me why you can just say that phi is equal to EA. Right? It isn't always. If you don't pick a good Gaussian surface, it won't be. Right? And what E and what A is also what we're wondering about too. And so, anyway, so phi is equal to EA. That's also equal to Q enclosed over epsilon naught. And so Q enclosed now is going to be rho times the volume of the wire, or of the cylinder thing. So it's going to be rho times pi big R squared times L. Right, so little r is now bigger. It's out here. The Gaussian surface is larger than the cylinder, but the volume that has charge in it isn't increasing anymore. As this is getting bigger and bigger, farther and farther away, it's still that same fixed amount of charge. You know, that is the size of the thing. So Q enclosed is that. And A is still unwrapped cylinder, so 2 pi little r times L. All right, so E, so this gives us E. We can just keep it as a vector and put an r hat on the end here, but E is Q enclosed over A epsilon naught r hat, which is rho pi big R squared L over 2 pi little r L. So pi's cancel, and don't forget epsilon naught. L's cancel. And so E is rho r big R squared over 2 little r epsilon naught r hat equals E as a vector. All right, so this is for r bigger than, little r bigger than big R. This is for little r less than big R. Give an expression for the electric field r less than r if the orange cylinder is a conductor with surface charge density here. Okay, so now if this is a conductor, what does that mean? That means all the charge will sit on the outside. There won't be any charge on the inside. And the field inside the conductor is always 0 in static conditions. And so electric field less than, okay, so inside here, Q enclosed equals 0 for a conductor, right? Because it's all on the surface. So when little r is less than big R, it's inside here, no Q enclosed. So that means that that EA equals 0, and so that means A is not 0, so that means E must be 0, and which we knew E is 0 inside a conductor. So probably accept either argument, but since we're talking about Gauss, it's good to do the Q enclosed argument. Okay, give an expression now for the electric field if little r is bigger than big R for the conductor, surface charge density, blah, blah, blah. Okay, so now if we're outside of it, now we do have some charge enclosed. Q enclosed is the surface charge density times the area of the surface that has a charge on it. Right? In this case, it's the area, the kind of unfolded area of the cylinder. So it's going to be sigma times 2 pi big R, the circumference up here, and then it's got the height L times L. Okay? Again, still same good Gaussian surface. So we've got phi equals EA equals Q enclosed over epsilon naught. So E equals Q enclosed over A epsilon naught. Make them vectors, put a unit vector on there. And Q enclosed is that sigma 2 pi big R L. And A is area of the Gaussian surface, right, where we're looking at the field. And so this is going to be the circumference of that circle, 2 pi little r, and then times the height, L. And don't forget epsilon naught. Alright, so the 2 pi's are going to cancel this time, and the L. And so E is just sigma big R over little r epsilon naught r hat. Okay, there we go. Let's look at number 6. Assume a very large conducting plate with surface charge density 10 microcoulombs per square meter, a cylindrical Gaussian surface, radius little r. Kind of hard to see there, but it's shown in 3D and has a 2D cross section, and has a 2D cross section here. So the cylinder is poking through the surface, sticking out each side. On the 2D figure, draw and label at least 6 arrows to indicate the direction of the electric field. Okay, at least 6 arrows. So we've got a very large conducting plate, surface charge density. So the field goes away from positive charges. So we got positive charge on the plate, and I guess on both sides. And so the field is going out like this, away from the plate. Okay. And what else is in here? I guess we can label it E. Alright, going off in both directions. Okay. What is the flux through the curved sides of the Gaussian surface? So the curved sides here, right, so for example, going up this way would be a dA out this way. So it's a cylinder, but it's a circle going around like this would be its A's, right? And so since the field is this way and dA is that way, we've got theta equals 90 degrees between dA and E everywhere on that curved surface, right? If you're looking at here, if we looked at it straight on, it would be a circle. E is coming straight out, and the dA's are going all around like this. E would be straight out at you. So they're perpendicular, so that means that cosine 90 degrees equals 0. And so phi equals EA cosine 90 is also 0. So flux equals 0 on the curved side. Use a given Gaussian surface to find an expression for the magnitude of the electric field near the plate. Alright, so if we want to say we want E here or here, we'll just say what is E right here on the flat top of the can kind of surface. Alright, that's the only place where we have a field, and then that area vector is straight out, and so is E, so they are parallel. And so on the top and bottom, or on the ends, E is parallel to dA, and E is constant. All right, assuming they're both, the whole end is the same distance from here, and so the E is going straight, so it's at the same. So E is constant on A, So then we got, again, a good Gaussian surface, so phi is equal to EA. And that's Q enclosed over epsilon naught. In this case, our surface has we have two surfaces to get our total A. Right, two surfaces that have flux. And so we will have E equals Q enclosed over A total epsilon naught. And what is Q enclosed? Let's get some pieces here. So Q enclosed. So this is a surface charge density. I wonder how I took that. Alright, so it's just like a very thin plane of charge. So it's just got, like, there's only one single row of charges, so we're not going to take it like two surfaces that have charge on both sides. It's just one little sheet, very thin sheet of charge, right? So Q enclosed is just going to be that sigma times A. Alright, so we're just going to take a cut out of this, and the charge inside there will be the Q enclosed, and so that'll be this area times the charge per unit area. Okay, so I'm talking A is the that's what it says. A is the surface area of the end of this cylinder, and the total area, though, for this that has that flux is going to be 2A. So A total equals 2A. All right. So then E. So E, we can E then Q enclosed sigma over A, and then divided by A total, which is 2A and times epsilon naught. So the A's are going to cancel. So we got E. Do we want to write it as a vector, or just write it as E? I guess we'll write it as a vector. We'll just kind of give a generic, straight out. We had to know that to do all of this. So sigma over 2 epsilon naught, and we'll just put an R hat on there just to show that it is a vector. We need to worry about the direction if we're going to actually find the value. All right, so this is a little different than if we had a conductor with just a charged surface density. This goes both directions, and so it's on both sides, and so it gets divided by 2. Which is a little different formula than what we have on our equation sheet. Okay, and then part D. Find the electric field from at a point 6 centimeters from the plate. All right. Well, the electric field anywhere from the plate, there's no R in here. It doesn't matter how far you are from the plate. Everything is very, very large, and basically we're assuming that the distance from the plate is small compared to the plate itself to get this kind of a result. So the electric field is going to be sigma. Well, it's going to be sigma over 2 epsilon naught R hat, where sigma is 10 times 10 to the negative 6 coulombs. 2 and epsilon naught is 8.854 times 10 to the negative 12. What is that? Coulomb squared per Newton meter squared, I think. So we got 10 e negative 6 divided by 2 times 8.854 e negative 12. Okay, 565 times 10 to the third newtons per coulomb. We'll just have a generic R hat. In this case, it means just straight out from the plate. Okay. Number 7. Use a diagram below to answer the following questions. Alright, so we've got a dipole kind of thing going on here. Sketch the electric field lines caused by the charges on the diagram below. Maybe it's not a dipole. Maybe we're just looking at it. Okay. Electric field lines caused by the charges. So electric fields always come out of pluses and go into negatives. So electric field would come out of here and go that way. They got to come out in all directions from the charge, and they're coming in all directions to this charge. So they'd be going around like that. And anyway, it's kind of hard to, they kind of split up and come back in. Get a few more drawn in here. We get the idea. But they're all coming out of the plus and going into the minus. What a mess. Okay. Write an equation for the force on the positively charged particle. Include the direction vector. So force, Coulomb's law, we started with, force from minus to plus, everyone's going to do that, is K Q1 Q2 over R12 squared R12 hat. I'm going to do the generic version. And in this case, Q1 and Q2 are the same. Alright, so it would be Q squared since they're the same size, and R is given as D, so it's going to be D squared on the bottom. And what direction do we have? So we're talking about equation for the force on the positively charged particle. So the positive charged particle is going to feel a force. It's going to be attracted to the negative, so the force is going to be like this, F minus to plus. Alright, so we can just multiply by I hat, assuming this is the normal kind of X and Y kind of coordinate system. Okay? And in which direction would the positively charged particle move spontaneously? Well, in the direction of the force, so it moved to the right. Sketch the equal potential lines through points A, B, and C on the diagram. So here's equal potential lines. Remember we did this in lab. Where's point C? Oh, point C is there. And so they are perpendicular to the field lines. Over here in the middle, it'd be kind of roughly straight up and down. And then over here, it might be kind of an egg shape, kind of things like this. So these are the equal potentials. Okay, like we did in lab. Okay. 8. Consider the balloon with a charge of 7 microcoulombs centered 15 centimeters directly above a conducting ball with a charge of 4 microcoulombs and a mass of 3 grams. Treat the balloon and ball as point charges. Include vector directions. What is the electric field at the ball due to the balloon's charge only? Alright, and so this is negative, this is positive, so it's going to be attractive. So the electric field from the balloon would be pointing straight up right there since it's straight below it. And so E from a point charge, KQ over R squared, R hat in general. In this case, it is K 8.9876 times 10 to the positive 9th Newton meter squared per Coulomb squared, and Q of the balloon 7 times 10 to the negative 6 coulombs over R squared. The distance is 15 centimeters, so 0.15 meters squared, and the direction is up, J hat. I guess we can get a number. 0.976 E9 times 7E negative 6 divided by 0.15 squared. Pretty big. 2.79. Let's just go with 3 sig figs here. 2.80 times 10 to the 6th J hat newtons per coulomb is E balloon, I guess I called it. Alright, check number here. What is the electric force on the ball? We did this a lot of times, so hopefully you're going to know how to do this. Electric force on the ball, F equals QE. Hope everybody gets this on the test because we've done a lot. So that's QE. The ball's the test charge. The ball's the one feeling it, so its charge that is the one that we're going to put in this equation. So it's 4 times 10 to the negative 6 coulombs for the ball. And it's in the balloon's electric field, which is 2.80, 10 to the 6th J hat newtons per coulomb. So we got a positive 6 and a negative 6 multiplied, so they'll go away. And so we have 4 times 2.8. So the force is 11.2 J hat newtons as a vector. Okay. Will the ball rise up toward the balloon? Well, if it's not too heavy, right? So how can we figure out if it's not too heavy? Well, we got to figure out what is mg, right? What is the weight of the balloon? All right, and we're given the mass, so mg, or the weight, weight of the ball. What is the weight of the ball? M is 3 grams, so it's got to be 0.003 kilograms. Standard unit for mass is kilograms, and times G, 9.81 meters per second squared. And so the weight of the ball will be 0.003 times 9.81. Wow, okay, that's tiny. Okay. 0.029 newtons. Yes. All right, so yes, it will rise. It would rise because F is greater than mg. F, yeah, the magnitude of F is greater than mg by quite a lot. Okay. Consider a 5-gram tinfoil ball suspended by a string with a charge of 2 nanocoulombs and a rubber balloon with a negative 4 microcoulombs charge. Treat the balloon and ball as point charges. Okay, how far away from the ball should the balloon be held to get a horizontal force of 5 millinewtons? Assume the balloon is held level with the ball at all times, and the ball and the balloon do not touch. Okay, so it's going to be attracted, so it's going to be pulled over here somehow, but we're going to go ahead and raise the balloon up so that they're straight across here, and we're asking for how far does it need to be to get a force of 5 millinewtons. Okay, so if we're going to do a free body diagram of the little tinfoil ball, it's going to have an mg. It's going to have a electric force, F, let's call it F, and it's going to have tension from the string here, right? And we want to know D. Okay, so we got some angle here. Call it theta for now. And we've got to use Newton's law. So Newton says this thing is sitting still, it's all balanced, so the sideways all the sideways forces add to 0. So sum of the forces in the x direction equals 0. Well, equals ma, which ax is 0. So equals 0, and the sum of the forces in the y equals 0 because may equals 0. And so adding these up, well, the whole force of tension is T. It's going to have a Tx part and a Ty part. All right, so summing the forces in the x direction says that Tx equals F. So we could say negative Tx plus F equals 0. So Tx equals F. Tx equals F, and then this one says that Ty is going up and mg is going down, so Ty equals mg. Oh, I didn't leave enough room to do this problem. Okay, so we also know that F is from the electric force, so it's going to be KQ1 Q2 over R squared, where R is actually D. And the direction it said that we're just going to keep it so that it's completely horizontal. So we'll have the whole of F is horizontal, so we don't need the unit vector on here. So we've got D in there to try to solve for it. We've got the Q's, yes, we know K. So, but we don't know Tx and Ty. But we've got two equations. We may have too many unknowns. Okay. Oh, wait a minute. We're not asking for all of it. We're given F. Okay. I'm doing too much here. All right. So let's take a little side route. So we're given F. All right. So F. Okay. So F is just K Q1 Q2 over D squared. So D is square root. Bring D squared over here, divide by F, K Q1 Q2 over F, and we have all these things. 8.9876 times 10 to the 9th, square root of that, and we've got 2 times 10 to the negative 9, and 4 times 10 to the negative 6. Oh, what a mess. Divided by F, which was 3 millinewtons, or 5 millinewtons, 5 times 10 to the negative 3. All right, so D square root of 8.9876 E9 times 2E negative 9 times 4E negative 6. That divided by 5E negative 3. Okay, so we get 0.120 meters. Okay, and so that's the answer for up here. That's a mess. For part B, what will the angle of the string be with respect to vertical under these conditions? So now we can use this. Maybe, yeah, kind of. Okay, so we've got, what is Tx in terms of theta? The angle with respect to vertical. All right, so the angle of theta is here or there. So theta compared to the vertical is the adjacent angle, right? So Ty is T cosine theta, and Tx is T sine theta, because the x component is opposite the angle. All right, and so we've got that Tx is equal to F. So Tx equals F, and so So T cosine theta equals equals 5 times 10 to the negative 3 newtons. And we've got Ty equals mg. So T sine theta equals m 0.005, 5 grams, 0.005 kilograms times 9.81. So if we flip these over and divide, so take this divided by that, we can get tangent theta and the t's will cancel. So we get tan theta equals 0.005 times 9.81 divided by 5 times 10 to the negative 3. And so theta is inverse tangent of that. 0.005 times 9.81 divided by 0.005. Okay, so those cancel. So inverse tangent of 9.81. $84 point. Okay, not right. Okay, sorry. That's 84 degrees is a huge angle. It should be the opposite. I've got the wrong angle because I screwed up my signs and my x's and y's. Tx is the sine. Ty is the cosine. All right, so tangent theta, divide these two equations by each other, so this becomes, the t's cancel, we get tangent theta is equal to 0.005 for this one, divided by 0.005, 9.81. So theta is tan inverse of 1 over 9.81. Tan inverse 1 divided by 9.81. That's more like it, 5.8 degrees. Oh boysies. What is the electric field at the ball in the final condition? Okay. Electric field at the ball, just from the balloon, I'm sure is what it's asking for. Let's just make ourselves a little place here. What a mess. So electric field is, we can do KQ over R squared. Would that be the easiest? Or can we just do force over charge? So E is force divided by charge. We got the force, 0.005 newtons, and the charge of the ball was 2 nanocoulombs, 2 times 10 to the negative 9 coulombs. So the field is going to be 0.005 divided by 2e negative 9. 2.5 times 10 to the 6th newtons per coulomb, and it is pulling that away, so it'll be I hat. Okay, so you could do it that way, or you could do KQ over R squared. Better get the same number. Okay. So this test is quite long for being a 1-hour test. It's not meant to be a sample of how long it is. It's just giving you the kind of problems you can expect. Some of the types of problems you can expect. Again, there could be other types, but this is just giving you some samples. Okay, continuing on. Consider a dipole of charges, positive and negative 2 nanocoulomb, separation of 3 micrometers. assume the dipole is oriented on its axis with a 30-degree angle to the horizontal XZ plane with the positive end up and the center at the origin. A uniform field directed straight up. Whew, okay, let's see. So we got the field is going straight up. We got our in the Z direction. So Z is up. And we've got X coming out, let's say, and Y going that way. Okay. And we've got our dipole. Axis at a 30-degree angle to horizontal in the XZ plane. So it's doing something like this in this plane with the plus end up and the center at the origin. So it's going through there down to that side. Ooh, it's hard to draw. We got a plus here and a minus here. 30 degrees to the horizontal. So the 30 degrees is in here. Yikes. Okay. So, and E is uniform 500 newtons per coulomb. What is the dipole moment as a vector? The dipole moment goes from negative to positive, goes that away. And so let's draw it like this so we can see a little bit better. So we got Z and X and Y is coming straight out now. And so we've got our dipole sitting in here like this. Or we got 30 degrees here, the plus here and the minus here. Alright, so the dipole moment P is equal to Q times D. Q is just the charge of one of the poles, so it's 2 times 10 to the negative 9 coulombs. And then what is D? D, we have a separation, yes, so this whole thing is 3 micrometers. We've got this angle is 30 degrees, and so the total displacement from here to here is going to have a x component and a z component, right? And so the x component is going to be 3, x is this way, all right? So this is dx, and this is going to be, say, dz. All right, so it's going to be 3 cosine 30 degrees I hat 3 micro, and then the z component is going to be 3 micro sine 30 k hat z direction. Whew. Okay, so P is 2e negative 9 times 3e negative 6 times cosine of 30. So, small numbers here. 5.1, 5.20 times 10 to the negative 15 I hat plus 3e negative 6 times 2e negative 9 times sine of 30. 3 times 10 to the negative 15 k hat. Oh, coulometers. All right. Just double check my numbers here. Yep. It is not centimeters. It's coulombs times meters. When I first looked at my other sheet, it looked like centimeters, but it's coulombs times meters. I'll probably do times in here. Weird looking units. Okay, what is the torque on the dipole? Torque is P cross E, or is P E sine theta, where theta is the angle between the two, from P to E. Okay, let's do that in terms of magnitude, and then the direction. So what would be the direction? The dipole is sitting in here, and the field is straight up in the z direction. All right, so we got P cross Z going straight up. So if we're looking at this picture, it would be going in the negative J direction, or negative Y direction, so it would be a negative J hat kind of direction. What is theta in this case? Theta is the angle from, this is P, and this is, and then E is up here going straight up. So the angle here is theta. This is 30 degrees. The whole thing is 90, so theta is 60 degrees. All right, so the torque is P, magnitude-wise, square root of 5.20 squared plus 3 squared, 10 to the negative 15, and then times E, 500, and sine 60 degrees times negative J hat. Alright, so the torque is square root 5.2 squared plus 3 squared times 1e negative 15 times 500 times sine of 60. 2.60 times 10 to the negative 12 negative J hat Newton meters. Okay. I don't see a number. Well, I think it's good though. Okay. You can double check me. If free to move, how will the dipole move? Rotate about its center, rotate and go up, rotate and go down, go straight up with no rotation, go straight down with no rotation. It won't move at all. Well, its moment isn't lined up with the field, so it's going to move to line those up. It's going to rotate in the XZ plane and go straight up. The net force, since it's a uniform field, there's no net force on the thing because it's pulling up as much on the positive as it's pushing down on the negative. So it won't move up or down. It's just going to rotate. And so it's going to rotate and go up. Rotate about its center. I think that's the only one that works. Okay? If the field was instead caused by a 20 microcoulomb charge on the z-axis at 10 centimeters, how would the dipole move? Draw a diagram and explain your answer. Whew, okay, so if we had the dipole, if we had a charge up here that was causing the field, what would the field look like? It would be going out. Oh, it's a negative. So it would be going up, in. Right, the field would be going 3D, but going into that. And then the dipole is sitting here with its positive up and its negative down. And so this is a negative 20 microcoulombs. And so it would have some rotation to get lined up with the field, but it would also, the positive charge is closer. So the positive charge is going to be attracted, the negative charge is going to be pushed away, but the positive charge is closer. It's not a uniform field anymore. And so the positive charge is going to be attracted, so now it's going to go up It'll rotate and go up. Rotate and go up. Okay. Okay. Consider a surface in an electric field as shown. Assume this. Excuse me. Assume the surface is 10 centimeters by 20 centimeters in size, and we want a flux of 25 Newton meters squared per coulomb. What must the strength of the field be? So flux, if we're uniform, we don't need to do an integral. We can just say it's EA. It's E dot A. So it's EA cosine theta, where theta is the angle between E and A. A direction is normal to the surface area. So A is like these little ends that are shown here. So theta is 30 degrees in this case. So we want this field, so we got 25 standard units, Newton meters squared per coulomb, equals E, that's what we're looking for. We're just doing magnitudes here. A is 10 centimeters, 0.1 times 0.2, this is a square, meters squared, meters times meters, and cosine theta, cosine of 30 degrees. So E is 25 over 0.1 times 0.2 cosine 30. <clears throat> 1.44 times 10 to the third newtons per coulomb is the magnitude of E. Write the field and area vector in 3D vector notation. We got this XYZ stuff going on again. Okay, so these are in the XZ plane, it looks like, again. And so the area vector is 0.1 times 0.2, and then it's in the positive y direction, j hat. All right, so 0.1 times 0.2, 0.02, 02 j hat square meters is A, the vector A. And then the area vector, that's the area vector. And then write the field vector. So the field vector, it looks like it has no x component. It's just going in the z and the y, right? And so we got, it's like this, where we got, this is EY, and this is EZ, and this is 30 degrees. So this is E. And so we can say E, didn't leave much space here. So E is magnitude of E, which is this 1.44, well, 1440, times cosine 30 j hat plus sine 30 z direction k hat. So 1440 times cosine 30 987 j hat plus 1440 times sine 30 720 k hat equals Newton, or newtons per coulomb is E as a vector. Write an expression for the flux using your vectors to check your result. Flux equals E dot A, I guess is what we're wanting us to do, E dot A. So it is 987 J hat plus 720 K hat dotted with 0.02 J hat. And so when you do the dot products, you just do I times I plus J times J plus K times K. And so all we've got is, so it's going to, the J times J is 0.02 times 987 plus 0, well, on the X, 0 times 0 plus Y's, those two, and then the Z, 0 times 720. And so the flux, 0.02 times 987, 19.74. Yikes. What did I do? I got the wrong number here. I did 1140 times cosine theta. 1440 times cosine of 30 is 1247, not 987. 1247. 1247. 1247. 0.02 times 1247. 24.94, which is about 25. We got rounding errors happening. Newton meters squared per coulomb. So we'll say good enough. Okay, so that is sample test 1. Like I said, it's pretty long. It's long for an hour test, so, but it gives you the idea of the kind of problems, the kind of equations that you need to know, the kind of things you need to understand. So we'll stop there.